Thank you for watching the video for my poster presentation. Knee ligament injuries are highly prevalent in the US, leading to significant financial and social losses. Ligament failure is caused by damage to the collagen fiber matrix of the tissue. However, current imaging techniques capable of detecting this damage are invasive and undesirable in the clinical setting. We need to develop non-invasive methods to characterize damage in knee ligaments. Diffusion tensor MRI is a promising non-invasive imaging method that quantifies the diffusion of water molecules in a material. Because it is sensitive to physical barriers, such as cells and fibers, it can provide an indirect measure of tissue microstructure. However, there is an unclear link between DTI and tissue microstructure due to the high heterogeneity of knee ligaments and biological tissues in general. We propose the use of more homogeneous ligament-mimicking fibers that we have previously developed as microstructural DTI phantoms to circumvent this issue. The objective of this study was to evaluate the effect of fatigue loading on microstructure and DTI metrics of our phantoms. We subjected a group of 5 phantoms to fatigue loading and compared them to a control group of 5 phantoms. We collected the mechanical data for the fatigue loading, and after that, we obtained high-resolution images and micro-CT scans of both groups of phantoms to obtain measures of fiber microstructure in the phantoms. After that, we submerged the samples underwater and conducted diffusion tensor imaging to obtain the principal diffusion direction on the phantoms, which is the direction of preferred water diffusion in the material, and the Z orientation angle, which is the angle between the principal diffusion direction and the main axis of the phantoms. We found that fatigue loading increased the mat strain and linear stiffness of the phantoms, as it has been previously seen in knee ligaments and tendons, and that fatigue loading decreased the phantom diameter and the ply twist angle, increasing the fiber alignment and the fiber density in the fatigue phantoms compared to the controls. Most importantly, what we found with the DTI data was that there was less axial diffusion in the fatigue samples compared to the control samples. How is this possible? You may be asking yourself. Well, what happens is that there were local regions in the fatigue samples where we found a disrupted principal diffusion direction. What this says is that there are some specific regions of the fatigue samples where we can have a disrupted fiber microstructure caused by fatigue damage that we were able to detect using diffusion tensor imaging. Hence, from this data, we conclude that diffusion tensor MRI and the principal diffusion direction that we measure from it can be used to identify local microstructural disruptions in fiber architecture that are caused by fatigue loading. This has very important implications because we can use DTI as a measure to characterize damage in knee ligaments non-invasively. Thank you for your time watching this video, and please reach out to me if you have any questions. I hope you enjoyed the conference.